Hello everyone and welcome to Mr. Saucedo's YouTube videos. Today we're going to be going over chapter 12 in Zumdahl Chemistry, the 7th edition. It's all about chemical kinetics, so let's get started. So section 12.1, reaction rates. What is a reaction rate? Well, a reaction rate is the change in concentration of a reactant or a product per unit of time. And so you can think of it mathematically as we're basically doing a change, right? So it's a change in the concentration of A from time 2 to time 1 divided by time 2 minus time 1. So we're looking at the overall change of whatever A is divided by the overall change in what the time would be. And again, A can be either a reactant or a product, and it is normally measured in the unit of molarity. So we're normally looking at moles per liter. So let's look at a decomposition reaction where we're looking at nitrogen dioxide turning into nitrogen monoxide and oxygen gas at 300 degrees Celsius. So this is some data that you would be able to find or collect about the decomposition rate of nitrogen dioxide. So notice that at time 0, we start with a full amount of nitrogen dioxide and almost no, it's 0, so it's exactly no. And we have absolutely no nitrogen monoxide and we have absolutely no oxygen gas. But after, 50 seconds, that has now changed. And now we are decreasing in the amount of reactant, in this case, nitrogen dioxide, and we are now increasing in the amount of nitrogen monoxide we've been making and the amount of oxygen that we've been manufacturing. Okay? And so if we were to graph this, this is what we would see. We would see that we have, again, at time 0, 0 products, and we have a full amount of reactant. And then as time goes by, that starts to decrease. And each of these little points is some measurement that was taken along the way. And then you connect the dots with a curve here. And these are the curves that you get. Okay. And again, that makes sense, right? That we should be slowly gaining more nitrogen monoxide and oxygen and we should be decreasing the amount of nitrogen dioxide over time as the reaction continues. You can probably tell, though, right, that if we were to continue doing this, eventually these would flatline and we would end up, with this decreasing to a particular value and these would be increasing to a particular value. But you can kind of tell, right, that they're going to flatline at some point, that they're not going to go to completion. And when I say completion, I mean not all of it is going to get turned into these two things. And that's important because we're talking about equilibrium. So what is the instantaneous rate then, right? That is the value of the rate at any particular time. And so the way that we obtain that is by computing the slope of the line that is tangent to the curve at that particular point. And if that sounds confusing to you, it's probably because you haven't done calculus yet. And that is totally and completely acceptable. It's not a requirement in order to do this that you already know calculus. But let me just give you the idea of what it's talking about, just so you understand what this means. So let's say I wanted to know what the actual value is at this singular point in time. So based on the data that we collected, one of the ways that we'd be able to figure that out, right, would be able to do a little subtraction. We'd be able to just take 2 points that are in between this, and we would be able to subtract them from one another and subtract the times from one another and divide the amounts of NO2 divided by the time difference between those two values. And that would give us a good approximation of what this value would be right here. Now, obviously, that's not perfect, though. If we were to get the exact point right here, we want to know exactly what that value should be. We could take an imaginary tangent line from this point. And so that's what this little, thin green line is. You can picture just that is running right through that point, and it's giving us this nice straight line. Well, then at that singular point, we could actually do the exact same thing. We could find the slope of that line, and right there, that would tell us the exact value of NO2. Now, are you going to be asked to ever do that? Not on the AP exam. But you get the idea behind it. The idea is that we can approximate it by subtracting, our concentrations and then dividing by the difference in time. But a better way of doing that would be to instantaneously find exactly what that number would be, which would be by drawing a tangent line and finding the slope of that line instead of just picking 2 other points on our curve. Okay. let's talk about rate laws. So what is the rate law and what does it show? So the first thing you need to be aware of is that it shows us how the rate depends on the concentrations of our reactants. So for the decomposition of nitrogen dioxide, we would end up with our balanced equation that we had previously that looked something like this, where we have 2 nitrogen dioxides, that's going to yield 2 nitrogen monoxides and 1 oxygen gas molecule. And so this is how we would write the rate law. So all rate laws look the same. It would be K times whatever your first reactant is, and in this case we only have 1, raised to some power. K being the rate constant and N being what we call the order of the reactant. So if it's a 1, that would be first order. If it's a 2, that would be second order. If it's a 3, that would be third order, etc. Right? Like you can just imagine if there's a 4th, a 5th, a 6th, etc. And so that's how we would write it. But here's the big problem. A lot of times people see the balanced equation and they say, oh, well, there's a 2. I'm just going to put this 2 right here. And now I know that I have a second order reaction. That is one of the biggest mistakes you can make, because that is not how you determine what the rate law is. Rate laws need to be determined experimentally. Notice that when we write this stuff down, so rate equals K times NO2 raised to the N power, there was no nitrogen monoxide, right? There was no oxygen molecule in our rate law. And the reason why is because we are only interested in the reactants. If there was another reactant, okay, your rate law might have, another reactant in it. We would include that. But again, we don't care about the products because we are assuming that this is a forward reaction, meaning that the reactant is being turned into products, and that very little product is going to be turning back into reactants. And also, remember what I just said, the exponent n does not come from the balanced equation. It has to be determined experimentally, and that takes time, and there are different methods of doing so. Also, why do we care? Why do we care about what the rate law is? It's important because from the rate law, we can infer the steps that are necessary in order for the reaction to occur, which is useful to us. And also, it lets us know time. How long does this reaction take? Because sometimes you might be like, oh yeah, this is a very simple chemical reaction. I can just mix these two things together. But then the rate law, when you actually look it up or find it or calculate it, it will take you days or weeks to do. And that would not be probably something you would want to do then. So the first method of determining the form of the rate law is called the method of initial rates. So the value of the initial rate is determined for each experiment. And that's what you actually do. You do a set of experiments to determine this. And you try to get as close to t=0 as possible. Obviously, your reaction needs to occur in order for you to get your data. So it can't be t=0, but you want it to be like, seconds after the reaction happens, or sometimes milliseconds after the reaction has happened. Several experiments are carried out, and we compile all of that information together. So you can picture this, right? I could do this initial reaction, let's say, with 1 mole per liter of my reactant, and then I can up it to 2 moles per liter. And then maybe I do a half, a mole per liter. And from that, I'm going to get different values for different amounts of products. And from that information, I would be able to figure out what the rate law is. So that's kind of interesting, right? It's just basically comparing data to other data, which is useful, right? And something that like all scientists do. You're comparing one data set to another data set after making one change. So overall reaction order. Now, a lot of times what you'll find is that you'll see something that looks like this for a rate law. The rate equals K times the concentration of A raised to N power times the concentration of B raised to M power. Now, how do we find the overall reaction order? Well, N and M added together gives us the overall reaction order. K is our rate constant, A is the concentration of A, B is the concentration of B. But something that I would also kind of add is sometimes they will just say, not what the overall reaction order is, but they'll say, what is the order with respect to A? And so in that case, it would be, they're basically asking, what's the exponent that A is raised to? Or they could say, what is the, order with respect to B? And that would be M. What is, the M, the exponent that B is raised to? So let's pretend, okay, I didn't type any of this, but let's pretend. Let's say that N is 1 and M is 2. So what I would say if I were describing this rate law to someone is I would say that the rate law is first order with respect to A, second order with respect to B, and the overall order of the reaction is third order overall. Does that make sense? So again, you could be asked individually what the exponents are, in which case you could say, oh, this is first order, this is second order, and then overall, when you add them together, that makes it a third order overall reaction. And so those are types of questions that might trip people up just because they didn't read it very carefully. So keep that in mind. The overall reaction order are all your exponents added together, but you could be asked individually, what is the reaction order with respect to A? What is the reaction order with respect to B? And so how do the exponents in rate laws compare to the coefficients in balanced equations? Hopefully you've heard this now 10 times, it seems like, right? The exponents do not have any relation at all. Sometimes you might be like, oh yeah, like there's a 2 in that balanced equation and it ended up being second overall. That's purely coincidental. The fact that a balanced equation gives you a certain number, that is just basically telling you that the law of conservation of matter or the law of conservation of mass is being followed. The rate law is totally different than the law of conservation. So let's talk about first order reactions. So K times A. There are different methods that we use to figure out, like I said, what is going on at any particular moment in time. And so the integrated rate law is what it's called. And the integrated rate law is the natural log of A equals negative K times T plus the natural log of A sub O. What do these mean? Well, A is the concentration of A, at a particular time in the reaction. K is the rate constant. T is time, obviously. A sub O is the initial concentration of A. This is useful to us because without knowing any calculus, this is a calculus equation, and it gives us a very good and easy way of being able to find what K would be. And so let's pretend we have something like this. I wanted to plot, this is a first order reaction, I wanted to plot the natural log of dinitrogen pentoxide over time. And so I ended up with this negatively sloped line. Guess what this negatively sloped line equals? Negative K. So I don't actually have to do the method of initial rates, right? If I actually plot the data instead of using the law of initial rates, I can literally just find the slope of the line and that will tell me what K is. Well, technically it'll tell me what negative K is, but still from that, I can just get K by, flipping my, the sign on my slope. Simple as that. Now, so half-life is weird, okay? But keep in mind, the only half-life equation you actually need to know is the half-life equation for first-order reactions. So for second-order reactions and zero-order reactions, there are different half-life equations, but this is the one that you're actually used to seeing, especially when you did like nuclear chemistry and you were solving half-life problems, probably in your previous chemistry class. So half-life is equal to 0.693 divided by K. 0.693 might look familiar to you if you understand what natural logs are. And notice, right, that in this case, our rate constant, half-life does not depend on your reactants at all. So if you know the half-life of a first order reaction, you actually don't need to do any experiments. You could just find out what K is immediately instead, which is kind of useful and nice. All right, so let's try to solve a half-life problem that is first order. So we have 35% a reaction that is 35% complete at the end of 55 minutes. What's the value of K? So much easier than using a graph and finding the slope. All right, so 35% is going to be important to us, and so is 55 minutes. But here's the big mistake people end up making. Obviously, I'm going to have to use my half-life equation, right? What's going on with this? So keep in mind, okay, and this is important, that if a reaction is 35% complete, that means that there is 65% remaining, which is the big mistake that people would end up making. So I actually have to take the natural log of 0.65. That's going to be equal to negative K at a particular time, in this case, 55 minutes, plus the ln of, in this case, 1, right? Because we started at, 100% basically. And so that would be represented by 1. 65% would be 0.65. When I solve for K, I end up getting 7.8 times 10 to the negative 3 Yes, it's inverse minutes, right? That would be the unit for this. Now, if you were instead to do 0.35, which is what most people would probably plug in, you'd be off by like a factor of 10. I think you get to the -2 instead. So it's important to make sure that you understand what the question is asking before you start plugging in numbers blindly. So second order reaction. So it looks something like this, Ka squared. What does the integrated rate law look like? 1 over A equals Kt plus 1 over A sub 0 or sub O. A, again, is the concentration of A at a particular time. K is your rate constant. T is time. And A sub O is our initial concentration of A. Again, what does this look like? Y equals mx plus b, just like the previous one. So we're really looking again at lines. What if I were to plot, the natural log of a second order reaction? I get this weird curve, but guess what? If I do 1 over instead, I get a nice straight line. So again, finding the slope of this line is the easiest way to get what K is. What about zero order reactions? Now you might think, what about third order? That's really rare and doesn't happen very often. So zero order, though, does happen quite a bit, and it's where K is just equal to K. A is raised to the 0 power, so you just end up with a rate. There's no fancy stuff for this one. The integrated rate law is just A equals negative KT plus A sub O. Again, what does this look like? Y equals mx plus b. So we're looking at a straight line again. A equals the concentration of A at a particular time. K is the rate constant. P is time. A sub 0 is the initial concentration of A. Now, what do we think that line might look like? Well, guess what? It's nice, right? We end up with a nice straight negative slope. And so we can find K by just flipping our sign, just getting K all by itself. Now, how can we tell the difference between these graphs? Now, this is actually where it gets interesting, and this is very AP. They could say, hey, look, I have this. This is my rate law data, okay? I have A versus time, the natural log of A versus time, 1 over A versus time. Is this a 0, a first, or a second order reaction? Answer, well, this is 0 order, right? This is a negative slope. So again, if it's negative slope, it's either going to be one of two of these because only one of them gives you a positive slope. And then if we take a look at our unit here, or at our value, we have moles per liter. That's it. Not natural log, not 1 over, so this has to be 0 order. But let's see what that would look like if it was first. If it was first order, notice we have a negative slope. And again, it is because we are using the natural log of A that we get a negative slope. Everything else is curved. What about a second order reaction? Hey, look, if you have a positive slope, you know it's second order. And that's because it's 1 over A, and we get a positive slope here, and we have curves for the other two. And so this is probably one of the most AP useful things to actually summarize everything. And so here's a summary of everything you just learned. For a zero order reaction, this is what we get. For a first order reaction, second order reaction, these are integrated rate laws where this is our Y, this is our M, this is our X, this is our B. And yes, that continues for all of them. To get a straight line, this is what we need. Our slopes are negative for 0 and first order. There is positive for a second order reaction. And then remember, you do not need to know the half-life equations. The only half-life equation that you actually will be asked to use at some point is the first order one. So ignore these two. Now, let's actually do this. Let's say I have the reaction, A is going to products, whatever that might be. I have the initial concentration, 5. I know that K is 1 times 10 to the negative 2. Calculate A after 30 seconds passed. Okay. For a zero order reaction, what would that look like? Well, I'm using, again, just A. That's equal to negative slope times, again, we have 30 seconds have passed, plus my initial concentration. So what do we get? We get 4.7 moles per liter. What about for a first order reaction? Now I need to use natural log. Natural log of A would be equal to, again, negative. We have our rate constant, which is our slope right here, 30 seconds plus the natural log of 5. Notice you would need to get rid of ln of A, so you would need to take E raised to this amount. When you do, you get 3.7 moles per liter. For second order, a little bit more fun, right? We have to take our inverse at the end. We have 1 over A equals the following. Notice it's a positive slope. And then we have to flip A over at the end. So we'd have to take this entire thing over 1, and we end up getting 2.0 moles per liter. Does this make sense? Hopefully it does make sense, right? So a zero order reaction is just a rate. It is constant like that, right? For a first order one, you're going to be subtracting more and getting rid of more of it. For a second order one, you're going to be getting rid of even more. So it should be quote unquote faster, right? If that makes sense, you're losing more of it faster. Now let's get to the interesting part. Let's take a look at reaction mechanisms. So most chemical reactions occur in a series of steps. We call them elementary steps because when you add together all of your elementary steps, you get your overall reaction. And so keep in mind, this is all just definition-based stuff. So an intermediate is what we call something that is formed in a step and used up in the next step so that you don't actually see it in your balanced equation at all. They're a lot more common than you'd think because when we look at a balanced equation, we assume, right, oh, it's really easy. You just take these reactants and then they become products. But it doesn't tell you how that happens. Like, are all of the bonds breaking and then reforming? No, probably not. That would take a lot more energy than would be necessary. So in reality, we end up with things like this. So we have NO2 plus CO, so that's carbon monoxide, gives us nitrogen monoxide and carbon dioxide. Look, looks really easy, right? NO2 plus CO gives you this, right? Isn't that about as easy as it can get? Well, in reality, this happens in many steps. So you can see I have an NO2, I have an NO2, they bounce into each other. This takes one oxygen. So now I have NO3. Now you might say, hey, there's no NO3 in here. Yeah. And remember, NO3 doesn't really exist. NO3 is nitrogen trioxide, and it doesn't exist for very long. It is an intermediate. And so what do we get as a leftover? We get nitrogen and oxygen, so we get nitrogen monoxide. Hey, that's one of my products. Notice that then we have our hella oxygenated nitrogen here. It doesn't want to have these three oxygens. That's really unstable. So it'll just give its oxygen away to this carbon monoxide and become, once again, NO2, and that will make CO2. So notice this. I always think this is super interesting, okay? Notice that if we were to take this as a balanced equation, right, like this and this, NO3 appears on the product side, NO3 appears on the reactant side. Technically, they cancel each other out, which is why we never see NO3 in our balanced equation here. You might say, what about this NO2? Like, yeah, technically, this NO2 and this NO2 end up canceling. And so what's the overall reaction? NO2 plus CO gives you nitrogen monoxide and carbon dioxide. Notice that one of the nitrogen dioxides goes away. Nitrogen trioxide is an unstable intermediate. It goes away. So we do end up with this overall reaction, but it gives us the illusion, right, that, oh yeah, this is super easy. No, it takes 2 steps in order to get this, these products to form. It's a lot harder than it looks. So what we like to call these elementary steps are the molecularity of the reaction. And so a unimolecular reaction is a reaction that only involves one molecule, and that is a first order reaction. Bimolecular reactions involve the collision of 2 molecules. We call those second order reactions. Termolecular, now again, that's super rare, which is why we didn't even do third order reactions when we were looking at equations and stuff. It involves a triple collision, and it's very rare, but that's a third order relationship. So how do we figure out what is going on when we mix things together like this? Well, a couple of little important facts. A reaction is only as fast as its slowest step. So whichever step takes the most time, that is going to be how quick your reaction is. The rate determining step is the slowest step then, and it varies depending on what your rate law is and the molecularity of the overall reaction. And so I always thought of it as you're only as strong as your weakest link. You're only as fast as your slowest step. So what are the requirements? Well, here are the requirements for a good reaction mechanism. When we add the elementary steps together, we must get the overall balanced equation. The mechanism must agree with the experimentally determined rate law. And so what that means for us is we could have something like this. Right? We have dinitrogen pentoxide, we have nitrogen dioxide, and we have oxygen gas. So what would we do? Well, let's just take a look at the first part of this. I'm going to save the second part for later on, but this first part. The overall sum must equal the balanced equation. Okay, so let's take a look at some intermediates. NO3 appears here and here, but doesn't appear in our overall reaction, so that must be an intermediate. What else can we cancel out? This NO2 and this NO2 end up basically canceling out. And I think, let's see, anything else? Oh yeah, this NO and this NO, those cancel. And so now what if we were to add all of these together? N2O5 plus N2O5 gives me 2 N2O5s, exactly what I want here. I have 4 NO2s, right? So I have 1, 2, 3, 4, good. And I have an oxygen. So technically, this first requirement is followed by this. Okay, so now let's actually talk about this last part, how the mechanism must agree with the experimentally determined rate law. So this one's kind of hard to do because you haven't learned any of the actual little tricks we use yet. But let's do a second one where I will teach you the tricks. So first things first, let's take a look at a mechanism that looks a lot easier and has a slow first step. So what happens when we have a slow first step? Well, we always want to make sure that we don't have any intermediates. So let me cross out the intermediates there. These oxygens are going to cancel. Okay. So like, again, we have our slow step. We're only as good as our slowest step. And the slowest step is the first step. That's kind of nice. Notice that we only have one reactant here in our slow step. That means that the overall rate law for this mechanism, since the first step is the slow step, is just going to be equal to K times N2O raised to 1 power, because right here I only have one N2O. Now you might think, oh, what about this N2O? That's a fast step. We're only interested in the slow steps. And of course, because it's the first step, it makes it really easy because then we can just look and say, okay, whatever this says, that's what's going to be my rate. That's going to match my rate law immediately. Okay, so this is a first order reaction with respect to N2O. Overall, it is a first order reaction. Now what happens when we have a slow second step? So this was where it gets a little bit more complicated. So we have a fast step, which is an equilibria, and we have a slow step. Okay, again, you're only as good as your slowest step. But what do I notice here? If I were to write the rate law for this, I would have to write NO times NOBr2. Why is that a no-no? NOBr2 is an intermediate. You can't have an intermediate in your rate law because intermediates don't appear in the overall equation. So great, now because it's the second step though, I have to go back. Okay, now I have to look back. How did I make this NOBr2? Well, I made this NOBr2 from an NO and a Br2. Okay, great. So what would my overall reaction be? Well, I have an NO here. You're only as good as your slowest step, but I need to make NOBr2. In order to make NOBr2, I need these other items. So now my rate law would be this, K times NO raised to the second power, because I have two NOs, Br2 raised to the first power. So if I were to look at the overall reaction order, it would be a terp molecular reaction. Again, unusual, but that's what it would be. It would be third order overall, second order with respect to nitrogen monoxide, first order with respect to bromine. Okay, so if it's the second step, if the slow step is the second step and you have an intermediate, so if this was not an intermediate, if it was just, another reactant, perfect. Like I wouldn't have had to go back to the previous step at all. I could have just written exactly what that said and be done. But because it was an intermediate, I had to go back and see, okay, great, how did I make that intermediate? I made it from these two items, therefore they must be a part of my reaction mechanism. Okay, collision model. Now we're going back to easy stuff. Molecules must collide in order to react. And that's why terp molecular reactions are so rare, because getting three things to collide together is extremely difficult. So what are our main factors? Activation energy, temperature, the molecular orientation. That just means the direction that they are facing. And so, of course, you've seen activation energy already, right? When we did enthalpy and we were looking at thermochemistry stuff, we saw activation energy as like these little humps for endothermic and exothermic reactions. Those were our activation energies. Okay. Now, keep in mind, right, that you do need the right amount of energy to overcome and produce a particular chemical reaction. If you don't have enough energy, it takes right to the peak here. This is the amount of potential energy. So this is the amount of energy that has to be overcome in order for a reaction to just occur naturally. And what that means, by the way, so when we say that just means you have the right energy, that doesn't mean that they're facing the correct direction. The orientation of the molecules might also be a really important factor in whether or not a reaction occurs. So for example, here we have, NOBr. And notice that in order for this reaction to occur, the BRs need to be over each other. So if you have enough energy and the BRs are over each other, this bond here will break, this bond here will break, and will form a bond between the two bromides. And now we're just left with nitrogen monoxides. Now, again, the collision has to have enough energy. It must be equal to or exceed the activation energy. The orientation, the directions that they are facing are important. Now, there is an equation to find the rate constant called the Arrhenius equation. It's K equals A times, and that is E, raised to the negative activation energy divided by RT. Now, this is one of the only times where R is not going to be our usual R value for the universal gas constant. Instead, we're going to have to use different units. So it's not 0.082 liters times atmospheres per mole degree Kelvin. It's going to be a different unit, which is totally fine for us. Okay, A is a frequency factor. E sub A is our activation energy. R is the gas constant, but it has to be in joules. So the gas constant is 8.3145 joules per Kelvin mole. So it couldn't be liters in atmospheres. We had to put it in our energy unit in this case because we are dealing with energy. We're not dealing with, gas constant stuff. T has to be in Kelvin. Now keep in mind, right, we can rearrange this and get a slope. For some reason, this unit loves slopes of lines. So again, picture this, y equals mx plus b. Yay, we have a line equation again. And so you can graph, our y and our x here. We can take our, ln of k, we can take our 1 over t, and we'll get a nice straight line. And then from that, we can calculate what E sub A is because the slope is equal to negative E sub A over R. We just need to remove the R and we would need to flip the sign. That's all we would need to do. So let's actually do this, right? This is a rule of thumb that chemists actually use. It is called the 10K rule, okay? So generally speaking, a reaction rate doubles every 10K. So what must the activation energy be for the statement to be true, right? If we're going from 25 degrees Celsius to 35 degrees Celsius, and we're basically doubling the reaction rate, what must be the activation energy in order for that to be true? Well, to double it, it's just 2, right? We're just doubling the reaction rate. So it doesn't matter what the rate is going to be double, so it's going to be 2. So we take the natural log of 2 equals our activation energy divided by our R, and then we just subtract. We subtract 35 from 25, but we have to convert that to Kelvin, right? So we do our 298. We have our 308 here. When we do that, we're going to end up getting a value that is going to be pretty close to 53 kilojoules. Remember, this is in joules. So our rate, our gas, I keep wanting to call it gas law constant. Our universal gas constant, there you go, is in joules. So yes, to get kilojoules, that does require you to divide because joules, there are 1,000 joules in a kilojoule. Catalysts. A substance that speeds up the chemical reaction without being consumed. It provides a new pathway by lowering the activation energy. And so you're used to seeing this because in bio, they're all over the place, right? So you have energy needed for our activation energy without a catalyst versus our activation energy needed with a catalyst. So notice that the difference between your starting amount of energy your reactants have and the amount of energy needed to start the reaction is a lot lower with a catalyst. Now, how does this generally, kind of affect what goes on? Well, the amount of effective collisions. An effective collision is a collision that will, that means that it is in the correct orientation to cause your reaction to move on to the next step, right? So an effective collision here, these are the amount, this is the amount of in an uncatalyzed reaction, the number of collisions that with a particular given energy. Notice how big that difference is when you actually add a catalyst. Now we have a lot more collisions occurring that are effective. Heterogeneous catalysts are catalysts that are in a different state of matter. So if you're doing something with liquids, it could be a solid or a gas. If you're doing something with a gas, it could be a liquid or a solid catalyst. And so here are the steps. You really don't need to know the steps that it takes. But the idea is that if you have like a solid piece of metal, so heterogeneous catalysts tend to be things like platinum or palladium, what happens is your reactant will actually stick to the catalyst. And so either by sticking to the catalyst, it means that when another molecule, like in this case, we have a red little thing stuck to the heterogeneous catalyst here, and then you have this other molecule which is going to go right next to it, and then it gets close enough and in the correct orientation that it's able to stick, and then it kind of basically just breaks the bond apart, and it leaves as a result. That is kind of what happens with heterogeneous catalysts, is that you end up having things stick to the solid. And as a result of sticking, now you have basically these little targets that are facing up that allow things to react in a more stereotypically effective way. Homogeneous catalysts, they're in the same phase. And just to keep in mind, enzymes are examples of catalysts, right? They're just biological catalysts. And so homogeneous catalysts are things that tend to be like floating around in your solution. So let's say that you're doing, a reaction in liquids, it could be a liquid. You're doing a reaction with gases, it could be a gas that's floating around doing that. And so you have your starting materials, you have your catalyst, it brings them together, and then you end up making your product as a result. And that's it for chapter 12. So again, if you have any questions, make sure that you let me know. As usual, subscribe and like this video, and there will be more coming soon.